Lab 4, spring mass system. In this lab we use the Newton's second law of motion, momentum principle, and the energy principle. In this lab we examine the motion of a spring mass system which moves in both x direction and y direction, and construct a computer model and compare it with the actual motion of the system. The Newton's second law of motion is that the final velocity is equal to initial velocity plus F net over mass times delta t, and the momentum principle is delta p is equal to F net times delta t. We can also find the location of the object by using this equation. The final position is equal to initial position plus velocity of the object times delta t, and the energy principle is that the total energy of a system is equal to the sum of the kinetic energy plus gravitational potential energy plus spring potential energy. Performing an experiment on a spring mass system, the mass of the object is 0.40 kg. The initial velocity is 0 at a time 0 second, and the initial position of this value which we obtained from the tracker, and the stretch length of the spring is 0.70 meter. By using tracker we perform an experiment and we get the motion data from using tracker. Here we see that the spring will move both in x direction and the y direction. These are the values we obtain from the tracker. We use these values and put it into the Excel sheet and form a graph. This graph shows the position of the in x direction of the object, and the gray line graph shows the position of the object in the y direction. We construct a computational model by using VPython, but first we calculate the time period, which is the time required for one complete oscillation, and equal to the 2 times y times mass of the object over the stiffness under root, and we calculate the stiffness is equal to the 6.1 Newton per meter. Right? Okay. For a static equilibrium condition, we study that the force due to gravity is equal to the force due to spring, and we calculate the stretch length L0, which is equal to 0.0542 meter. We use these values put into the VPython. The ball mass 0.402 kg, ball position, the velocity, and the G value 9.8, the stiffness value 6.1, the stretch length 0.042 meter. Here the S, which is the difference of the magnitude of the L minus relax length. If the S is greater than 0, then the spring is stretched. If the S is less than 0, then the spring is compressed. Okay, we use the delta K, the total change in kinetic energy, is equal to half of mv square. The gravitational potential energy is equal to mgh, and the spring potential energy is half of k s square. What does it mean for your model system? Is the energy principle satisfied? My answer is yes, because that the total energy is equal to the sum of the kinetic energy plus gravitational potential energy plus the spring potential energy is equal to the 0. And by using VPython, we put these values here. K, the potential energy, gravitational kinetic energy, the gravitational potential energy, and the spring constant. The total time period we have oscillation have is 7.123 seconds, and the F net is equal to the force of gravity plus force due to the spring. Here is the kinetic energy, the gravitational potential energy, and the spring constant. When we run it, we will see we have a graph formed that the red line show the object position actual, and the blue line show the computational one. Then now by using the Python, okay, now we show the kinetic total energy is equal to sum of the kinetic energy plus gravitational potential energy plus the spring constant. Then by using Python, when we run it, we will see that the blue line show the kinetic energy, green line the kinetic gravitational potential energy, and this is the spring potential energy, and the yellow line shows the total energy of the system, which is equal to the 0. Now the second question is that using data obtained from the tracker, make two separate estimates of the oscillation period. First by estimating the period of oscillation from the X position data, and second by estimating the period of oscillation from the Y position data, which we calculate is for the X, the time period of the oscillation in the X direction is 1.651 second, and Y is 1.519 second. The effect, this is because the difference between the terms is because of the effect of the gravity is stronger in Y direction, causing the oscillation to occur in a short period of time. Here we see that there is a difference between the X direction and the Y direction. This is the end of this lab 4 how to